Good afternoon, everyone. Welcome to my presentation. My name is Campilho. I come from J.P.S.M.B. The title of this work is Mixed Mode Evaluation of Ductile Adhesive Joints by the Single Leg Bending Test. The other colleagues that helped me in this work were Ribeiro and Rocha, and the main objective of this work is to validate the fracture envelope used for the ductile adhesive using the single leg bending test. Here we can see the layout of the presentation. I will start by the objectives, then we have the experimental and numerical work. I will start by mentioning the materials and joint geometries, speak a little bit about the experimental estimation of the fracture envelope of the adhesive that we used in this work, which is a ductile adhesive, the R.D.S.G 2015. And then we are going to use cohesive zone modeling using the obtained fracture envelope and respective exponent from the experimental tests and perform validation with two typical mixed mode geometries, the single up joints and the double up joints. And finally, we will address the conclusions of this work. Regarding the objectives, first we are going to experimentally obtain the fracture envelope of a ductile adhesive by the SLB test and also by the knowledge of the pure mode 1 and pure mode 2 fracture energies, which were obtained in a previous work. And after that, we are going to use cohesive zone models to verify the applicability of the fracture envelope that we obtained experimentally by considering two mixed mode cases, single up joint and double up joint. For this validation, we are going to compare the maximum loads obtained by the joints, both experimentally and numerical, to try to see if the obtained data can be used for design and for prediction of the strength of the bonded joints. If this is correctly accomplished, we have validated the experimental fracture envelopes, and we have a set of data for this adhesive that can be used and can also be extended to other adhesives if these are also properly characterized regarding their mixed mode behavior. Beginning with the experimental works, the adherents, both for the single leg bending and single up and double up joints, were made of a high strength aluminum alloy, AW6082, with a heat treatment. And here we can see the experimental data that we obtained from bulk tensile tests regarding the stress strain curves. We can see the experimental curves and also the numerical approximation that was used for introduction in the finite element software. We can see also the summary of properties that we obtained from this experimental characterization, namely the tensile strength, the Young's modulus, the yield stress, and the tensile failure strain, which show, by the way, that this is an aluminum alloy with high strength and also with a large ductility of over 20%. Regarding the adhesive used in this work, which shows the R.D.S.G 2015, which is an adhesive which has an acceptable strength and also a very good ductility, especially in shear, we can see that the Young's modulus of this adhesive is close to 2 GPa. We have a tensile strength of almost 22 MPa and a shear strength of nearly 18 MPa, and we can also see the tensile toughness and the shear toughness of this adhesive. All these properties were obtained experimentally, but in order to simulate mixed mode geometries, we also need the power exponent for the power law that is used in cohesive zone modeling, so that we have a correct description of the mixed mode behavior of these joints. This is what we are going to perform with the SLB specimens. Here we can see the geometry of the SLB joints. the geometry and the dimensions. This is a mixed mode test geometry in which we have at the same time tension and shear at the crack tip, by the fact that the lower adherent is only supported by the right cylinder. So we have a mixed mode state at the crack tip. We can see the dimensions to the right, and what we want with these tests is first to obtain the P delta curves, including the maximum load and the respective displacement, to obtain the resistance curves, which will allow us to get G1 and G2, and then we will have to frame these two values in the fracture envelopes so that we can ascertain the proper crack propagation exponent so that we can use in cohesive zone models. We can see here, after much data analysis that is not shown here for the sake of brevity, we show here the final result for the fracture envelope for the R.D.S.G 2015. We can see the expression that gives us the power law criterion to be used to access mixed mode crack propagation in CCM modeling. We can also see a graphic that shows us the pure mode G1C and pure mode G2C, which are the values of the curves that meet the axis. So the G1C is about 0.54 Newton per millimeter, and G2C is around 3 Newton per millimeter. These values were obtained in previous works for the same adhesive, and then we have the experimental data points of G1 versus G2, in which every one of these points corresponds to an experimental test. So we have the 4 theoretical fracture envelopes corresponding to exponents of 0.5, 1, 1.5 and 2, and we can clearly see that the points are closest to the curve corresponding to the fracture exponent of 0.5. So we are going to take the pure mode data from this adhesive and also this exponent to simulate the mixed mode crack propagation in both single lap and double lap. This is what we are going to do now. So here we can see the geometry of the single lap joint specimens and the double lap. We can see that for the double lap we considered symmetry conditions, so only half of the model is presented, and we have also to the right a table with dimensions, which shows us that we have an adhesive thickness of 0.2 millimeters, which was considered fixed for all specimens. We also have a thickness of the adherents of 3 millimeters, a total joint length of 170 millimeters, and we have varying overlap lengths ranging from 12.5 millimeters to 50 millimeters. Here we can see the entry values for both the tensile and shear CCM laws to model the adhesive layer. These properties come from the pure mode characterization of the adhesive that I showed previously, and to add to these properties we only need the mixed mode criterion, which was considered as 0.5, as we saw from the results of the single leg bending tests. So these are the properties that we want to validate. We also considered 4 exponents to make a comparison of the results, although from the results that we got 0.5 will be the one that will have the closest results to reality. We will consider 0.5, 1.5, 1 and 2 exponents. And regarding the numerical work, it was carried out in Abacus, considering 2D models and plane strain elements with 4 nodes, CPE4, the reference from Abacus. We can see in this figure some details of the numerical models, namely the mesh with bias effects to have higher refinement at the overlap edges. We can also see the boundary conditions for both the single lap joints and double lap joints. For the single lap joints, we have clamping at one edge and pulling at the other edge, while restraining in the y direction. The boundary conditions for the double lap joints are much similar, but we also have the symmetry conditions, so that we can simulate only half of the model. Here we present some numerical p-delta curves, in this case for the single lap joints, one graph for each overlap length that was tested in this work, and in each graph we have the four exponents, the four mixed mode exponents. We can see that between 1 and 2 the results are more or less similar, but for an exponent of 0.5 we also have a smaller value of maximum load than for the others. So the next step will be to compare the maximum values of these curves, which is the Pmax, the PM, and we will compare them against the experiments to see if the 0.5 is actually the correct value to consider. We can see that comparison in this graph, in which we have only the average Pmax plotted against the overlap length. We can see the experimental results in light blue, together with the standard deviation. First of all, we have an increasing trend of the maximum load with the overlap length, which is normal on account of the increase of bonded area. And we can see the curves for the four different exponent criteria. We can see that the yellow curve, which corresponds to the 0.5 exponent, presents the closest results to the reality, while the criteria 1, 1.5 and 2 overshoot the experimental results by a high amount. So by this we can say that the exponent of 0.5 is validated for this work. Here we have the same results, but now for the double lap joint. Here we also have some differences between the 0.5 and the other three criteria, and we also have some plasticization of the adherents for overlap lengths of 37.5 and 50 millimeters. Plotting the maximum values against the experimental values, which is the curve in yellow, we don't have a high difference between them, but here we have to point out that the failure is being ruled not by the adhesive but by the plasticization of the adherents and consequent tensile net failure, which occurs at around 24 kilonewton. So in this case we got very similar results between all the criteria, but we know that here is not the adhesive that is working. So by the concurrent results of the double lap and the single lap joints, we can consider that the fracture exponent of 0.5 is validated. Here I just present a summary of what was already said during the presentation. First, we tried to define the most suited exponent for mixed mode crack propagation of the R.D.S.G 2015, and we did this by experimental tests considering the SLB geometry, which allowed us to plot the fracture envelope since we had available the pure mode results both in mode 1 and mode 2. We got a clear result that stated that an exponent of 0.5 would allow us to replicate the experimental behavior and the mixed mode behavior of the joints. We performed validation with single lap and double lap joints bonded with the same adhesive, and we had accurate maximum load predictions for all overlap lengths, although, as I said, for the double lap joints we had failures that were ruled by the adherence failure, especially for high overlaps. So as a final conclusion, we can say that the CZM technique, together with the correct choice of the mixed mode exponent to be used in CZM modeling, can provide us good results. So this means that the CZM technique can now be applied and can be extended for other applications, for other geometries, and is an accurate technique for the design of bonded structures. Thank you very much for the presentation and for the time taken to listen to this presentation. Thank you.